Hi everybody, and welcome to my YouTube series on anatomy and physiology. This video is meant to be an overview video. What that means is that it is a composite of all the shorter videos I did on this subject. I did this so that students could watch the full content in one sitting rather than just watching several different videos in a row. If there is a specific topic that you would like to revisit, you can either go to that specific chapter in this video or simply go to the separate shorter video I did on that subject. The links for those shorter videos that are included in this one can be found below. Let's begin. To begin our journey, let's talk about atoms. An atom is the smallest unit of matter that still retains the properties of an element. It consists of three main subatomic particles: protons, neutrons, and electrons. The central part of an atom is known as the nucleus. It is composed of protons, which are the positively charged particles found in the nucleus of an atom. They determine the element's identity and contribute to its atomic number. The nucleus also contains neutrons, which are neutral particles that help stabilize the atom by balancing the positively charged protons. Electrons are the negatively charged particles that orbit the nucleus at energy levels, which are also called shells. Electrons are involved in chemical reactions and bonding between atoms that occur in the outermost shell, or orbit, called the valence shell. Now that we understand the structure of atoms, let's talk about elements. An element is a pure substance made up of only one type of atom. Each element is represented by its symbol, usually the first letter or first two letters of its name. For instance, H stands for hydrogen, O for oxygen, and C for carbon. Elements are organized in the periodic table based on their atomic number and properties. The atomic number represents the number of protons in an atom's nucleus. It is a unique identifier for each element. For example, hydrogen has an atomic number of 1, carbon has 6, and oxygen has 8. Elements have unique physical and chemical properties that make them suitable for various applications. For example, oxygen is essential for respiration, calcium is crucial for bone health, and iron is necessary for oxygen transport in our blood. As we're studying anatomy and physiology, understanding elements is vital because they play significant roles in the human body. Oxygen is crucial for cellular respiration, and it's used to produce energy through making a molecule called ATP to power our body's functions. It is carried by red blood cells and distributed throughout the body. Carbon is the foundation of organic molecules, such as carbohydrates, lipids, proteins, and nucleic acids, which are the building blocks of our cells and tissues. Calcium is essential for muscle contraction, nerve transmission, and bone health. It provides strength and structure to our skeletal system. Sodium and potassium are two elements that are vital for maintaining the body's water balance and electrical impulses in nerve cells and muscles. In the intricate world of anatomy and physiology, all living organisms are composed of cells. These cells are in turn made up of molecules, and the building blocks of these molecules are atoms. At the heart of every atom are positively charged protons, neutrally charged neutrons, and negatively charged electrons orbiting around the nucleus. The fascinating thing is how atoms come together to form chemical bonds. There are three main types of chemical bonds: covalent, ionic, and hydrogen bonds. In a covalent bond, atoms share electrons, creating a strong bond between them. In fact, when you think of covalent, think of sharing. We even see this come up in other words in English like cooperate, co-parenting, and coordination. This type of bond is common in molecules such as oxygen and water. There are two types of covalent bonds: nonpolar and polar. Nonpolar is where electrons are shared equally and the molecule has a neutral charge. I like to think of nonpolar bonds as being like a couple that's in a really good relationship where both people share equally, like these two oxygen atoms sharing their electron equally. This forms the molecule of oxygen. A polar covalent bond is where electrons are shared unequally, resulting in a section of the molecule having a slight positive or negative charge. So, for example, the bond between hydrogen and oxygen that makes water. Here we have a bond between a hydrogen atom and two oxygen atoms. But the oxygen doesn't really share the electrons equally, so this bond is unequal, with oxygen getting the electron most of the time and only occasionally sharing it with the hydrogen. I'm sure we've all been in a relationship like that before, where you give and give but only get a little in return. Because electrons are negatively charged, this causes the oxygen atoms to be slightly more negatively charged overall, and the hydrogen atom to be more positively charged. While water is formed through a polar covalent bond between hydrogen and two oxygen atoms, the way water works is a little bit more complicated than this, because it also involves hydrogen bonds, which we will discuss in a little bit. Ionic bonds form when atoms transfer electrons, resulting in charged ions. Oppositely charged ions attract each other, creating a strong bond. An example is the bond between sodium and chloride ions in table salt, or sodium chloride. You can think of ionic bonds as being how opposites attract. I like to think of them as being bullies. For example, we have our little sodium ion here playing with its electron, and along comes the chloride and steals the electron and keeps it for itself. Hydrogen bonds are comparatively weaker than covalent and ionic bonds. A hydrogen atom with an electropositive charge from one molecule is attracted to an electronegative atom of another molecule. So let's go back to that example of water I gave earlier. While the bond between the hydrogen and oxygen is polar covalent, this leaves the hydrogen with a slightly positive charge because an electron isn't being shared with it equally. Because hydrogen has this positive charge, it is going to form a very weak bond with the oxygen atom of another water molecule. Remember, the oxygen atom is going to have a slightly negative charge because it is getting the electron more than the hydrogen. So in this case, the hydrogen bond is between these positively and negatively charged atoms in each individual water molecule. Think of this hydrogen bond as being very weak, almost like two pieces of Velcro sticking together, or like two people just sharing a brief hug. They don't last long and are easily broken. These chemical bonds are essential for life. They enable the formation of biologically important molecules. Water, a fundamental molecule for life, owes its unique properties to hydrogen bonding. These bonds give water its high heat capacity, cohesion, and ability to dissolve substances. Proteins are vital for various cellular functions. Their complex structures are shaped and stabilized by a network of covalent and hydrogen bonds. DNA, the genetic blueprint of life, forms a double helix held together by hydrogen bonds between complementary base pairs. In terms of overall strength, the prize definitely has to go to nonpolar covalent bonds as being the strongest type of bond there is. After that, we have second place to polar covalent bonds. The bronze medal would go to ionic bonds, and hydrogen bonds would be the weakest. So the next time you write that love letter to a significant other, don't talk about how your love is strong or will last forever. Tell them how your love is covalent. Chemical reactions are the transformative processes that occur when substances interact with one another, resulting in the creation or breaking of chemical bonds. These reactions are the foundation of life and are constantly happening within our bodies. Now, I understand that chemical reactions can be a little tricky to fully understand, and this video is meant for anatomy and physiology students, not chemistry students. So I'm going to try to explain each of the reactions I'm going to talk about today with some easy to follow examples. There are three main types of chemical reactions: synthesis, decomposition, and exchange reactions. In a synthesis reaction, two or more substances come together to create a new, more complex product. This type of reaction is crucial for building essential molecules, such as proteins, and promoting growth and repair in the body. So you can think of this synthesis reaction as being like where we take A and B and add them together to make AB. I like to think of a synthesis reaction as being like when you're cooking. You take various ingredients, then put them together in a recipe to make food, something more complex. Oftentimes, a synthesis reaction can produce a molecule of water when the new bond is formed, and we call this a dehydration synthesis. So in this case, we would take A and B and make AB plus water as like a byproduct. Decomposition reactions, on the other hand, involve the breakdown of a complex molecule into simpler substances. This process often involves adding a molecule of water to break a bond. So you can think of decomposition as the opposite of what I just told you about A and B making AB. In this case, you would start with AB and then break it down into both A and B. These reactions play a vital role in digestion, where enzymes break down food into nutrients that the body can absorb and utilize. I like to think of decomposition as what happens when you compost. Composting is a great way to put nutrients back into the soil if you have a vegetable or flower garden. You take leftover food items and other material and add water. Then over time, these items break down into nutrient-dense material that then can be put back into the soil. Exchange reactions involve the swapping of components between two or more molecules, resulting in the formation of new products. These reactions are essential for energy production, as seen in cellular respiration. This one can be a little tricky, but if you go back to my earlier example with A and B, you can think of an exchange reaction as being like taking AB and CD, and after they react, you create AC and BD. I like to think of an exchange reaction as being like a dance, where you pass from one partner to another. The people don't change, but the partnerships do. Chemical reactions in our bodies are facilitated by remarkable catalysts known as enzymes. Enzymes speed up reactions by lowering the activation energy required for the reaction to occur. Enzymes achieve this by forming temporary enzyme-substrate complexes, allowing the reactants or substrates to interact more efficiently, leading to the production of products. Chemical reactions are indispensable in maintaining physiological processes essential for life. Cellular respiration is a series of complex chemical reactions that occur in our cells, producing energy, also known as ATP, in a synthesis reaction from nutrients like glucose and oxygen. Metabolism relies on chemical reactions to convert nutrients into energy, as well as to synthesize molecules required for growth, repair, and regulation of bodily functions, all of which are done through decomposition reactions. Organic compounds are the building blocks of life, characterized by the presence of carbon-hydrogen bonds. These compounds form the basis of all living organisms and serve as essential molecules in various physiological processes. At the heart of organic compounds are carbohydrates, the primary energy providers for our bodies. From simple sugars like glucose to complex carbohydrates like starch and glycogen, these compounds fuel our cells, providing the energy needed for everyday activities. Lipids, often referred to as fats, are essential organic compounds with multiple critical roles. Triglycerides store energy, while phospholipids form the structural basis of cell membranes. Cholesterol, a lipid, serves as a precursor to hormones and plays a crucial role in cell signaling. Proteins are the workhorses of life, participating in almost every biological process. Composed of amino acids, proteins are responsible for enzyme catalysis, muscle contraction, immune function, and many other vital functions that keep our bodies running smoothly. Nucleic acids, such as DNA and RNA, are organic compounds responsible for carrying and transmitting genetic information. DNA, the blueprint of life, holds the instructions for building and maintaining an organism. RNA plays a crucial role in translating these instructions into functional proteins. So basically, the RNA takes the DNA and creates proteins. Inorganic compounds are a fascinating group of substances that do not contain carbon-hydrogen bonds. Despite their lack of carbon, these compounds are vital for life and support numerous physiological processes. At the core of inorganic compounds lies the most crucial molecule for life, water, or H2O. Water's unique properties enable it to play an indispensable role in maintaining homeostasis and supporting various physiological functions. These properties include its polar nature, which allows it to create hydrogen bonds, its high heat capacity, which allows it to absorb more heat energy before evaporating, and its excellent solvent ability, or the ability to break down substances into a solution. Another class of essential inorganic compounds is electrolytes, which are electrically charged ions. Ions are formed when atoms lose or gain an electron, which then makes them either negative or positive. Technically, we call negatively charged ions anions and positively charged ions cations. A good way to remember this is cats are positively adorable. We typically show that an atom is an ion by giving its chemical symbol with an addition or subtraction symbol afterward to show the charge. Some of the most important ions are sodium, which is crucial for nerve conduction, potassium, which is important in muscle contraction, calcium, in this case it loses 2 electrons, which makes it especially positive, which plays a role in maintaining fluid balance in your body, and finally chloride, which helps regulate pH levels in your body. Inorganic compounds also include minerals, which are vital for various physiological processes. Minerals like calcium, which is important for bone health, iron, which is important for oxygen transport, and magnesium, which is critical for energy production, are critical to the way our bodies function and are obtained through the foods we eat. In this case, calcium is pulling double duty by being both an ion and a mineral. Acids and bases are inorganic compounds that play a critical role in maintaining the body's pH balance. The pH scale measures the acidity or alkalinity of a substance. The numbers lower than 7 are acidic, and the numbers greater than 7 are basic or alkaline. Maintaining the right pH is vital for enzymatic activity and overall cellular health. If you enjoyed this video, please give it a thumbs up and share it with others. To keep informed about new videos being created, don't forget to subscribe to our channel and hit the notification bell. If you have any questions or topics you'd like for us to cover, feel free to reach out and let us know. Thanks for joining today, and see you in the next video.